Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture on material balances for multiple unit processes without reactions. In the last lecture, we saw an example problem where we used the overall system to perform the calculations and then used individual units and performed material balance calculations. Here are more example problems. So, here is one example problem where we will try to approach the problem slightly differently. The problem statement is you are asked to design an acetone recovery system having the flow sheet which is shown below. All the concentrations shown, both gases and liquids, are specified in weight percent in this special case to make the calculation simpler. You are asked to calculate A, F, W, B and D per hour. You are also given that G is 1400 kilograms per hour. So, the problem gives you many information. The first thing we need to understand for solving any of the multi-unit processes is where do we start? What system do we choose? So, here unlike the previous problem, we do not want to start with the overall system because not all information of the streams is known. If we were to choose the overall system, then we would have many unknowns which we cannot solve for with the equations which we have. So, for this reason we have to attack the problem in a slightly different way. Let us see where we can start. So, we have an absorber column which is called as a unit 1, which has a water stream and a gas stream entering, and you have an air stream and another stream called F which are leaving the system. Now, can we use this unit 1 as the system to work with? What information would we have? We can write total balance equations and component balance equations. So, how many component balance equations will we be able to write? So, for most systems except for a splitter, for any other system, we would be able to write as many independent balances as the number of components. Here how many components do we have? We have air, acetone and water, which means we can write 3 different balance equations, and there are only 3 different unknowns which need to be solved, which are W, which is the mass of water entering, A, which is the mass of air leaving, and you also have to calculate F, which is the mass of the acetone water mixture which is leaving. So, this composition which is given here is the composition of air which is leaving the system. Now, let us go about solving this problem. As in any material balance problem, the first step is to identify a basis. So, here we will use a basis of 1 hour because the problem statement asks us to calculate the mass flow rates, masses per unit hour. So, we have used 1 hour as the basis, and let us continue with solving the problem. As I explained earlier, we will use this system which is unit 1 as the system to start with. We will write a balance for unit 1 which is the absorber column. So, the total balance for unit 1 would be, you have input equals output as it is a non-reactive process at steady state. So, you have 2 inputs which are W plus G giving you an output streams which are A plus F. We already know G, so we can write it down as W plus 1400 equals A plus F. Now, we can write component balances. Let us start with the component balance for air. So, component balance for air would be 0.95 times G is equal to 0.995 times A. Air is entering through the gas phase which is G and leaving only through A. So, this is the equation we start with. So, using this equation we can calculate A, which is the mass of air leaving the system, as 1336.7 kilograms. We already know G as 1400, so substituting for G we can calculate for A. We can now write a balance equation for acetone. acetone balance would be acetone entering through gas and leaving through the acetone water mixture. So, acetone balance, which is input equals output, would then become 0.03 times G, which is 1400, is equal to 0.19 times F. As we already know the value for G, we can calculate F as 221.1 kilograms. Substituting the values for A and F in this equation 1, which is the total balance, we can calculate W as 157.8 kilograms. So, now if we go back and read the problem, what we would see is we have been asked to calculate W, A, F, D and B. One stream which we do not need to get any information about is this particular stream. So, this means we can actually calculate only B and D for the second part of the problem. We do not need to worry about this particular stream. So, what does this mean for us when we choose the systems? Based on the information given in this flow chart, we do not have the composition of this particular stream. As we do not know the composition or the mass flow rates of the stream, it would be very difficult to estimate what this particular stream would be. Thankfully, the problem does not expect us to calculate this stream. So, instead of trying to identify this particular stream, we can now choose a system which would basically engulf this stream. How would we do that? What would be the system we can actually draw, system boundary that we can draw to do this? So, let us not worry about this stream. So, what we will do is we will choose a system which is the distillation column plus the condenser. So, the system would basically look something like this. So, now you have F crossing the system boundary and entering into the system, and you have D and B leaving the system. This means we can calculate information about B and D using the information we have about F. So, let us start solving the problem. So, we can write total balances for the system chosen. So, the system of choice here is units 2 plus 3. So, for that let us write a total balance. So, the total balance would be input equals output, which is F equals B plus D. We already know the value of F. So, we can substitute it here and get B plus D as 221.1. Now, we can write component balances. So, we can write the component balance for acetone. This is the component balance for acetone, which would be 0.19 times F equals 0.99 times D plus 0.04 times B. Now, we have two equations, equations 1 and 2, which contain only two unknowns. So, these two equations can be solved simultaneously to get the values for B and D. So, B would be 186.1 kilograms per hour and D would be 34.9 kilograms per hour. So, using the right systems, we were able to solve for all the streams which have been asked for. So, this is a critical aspect when you are actually going to perform calculations for multiple units. Whenever you have multiple units, the biggest challenge you would face would be to identify the right system to study. As long as you choose the right system, then the process becomes as simple as a single unit process. So, let us look at one last example problem before we conclude this particular topic. So, here the figure shows the process for extraction of sugar from sugarcane. All the known data is given here. You are asked to calculate the composition of every flow stream and the fraction of sugar in the cane that is recovered. So, to do this, we need to get information about all the unknown streams. We have streams like D, F, E, G, H, K, L, So, many different streams have been labeled without information. So, we have some compositions given, but we do not know the mass flow rates for any of these. So, here how do we start? Where do we start? So, we could look at the simple problems which we have done earlier. So, the first strategy would be to start with the overall system. Will that strategy work here? Probably not, because you only have information about one particular stream, and every other stream we have no information about the flow rates, which gives you F, D, G and J and L. So, those are 4 unknowns in the stream. So, it will be impossible to calculate all the 4 unknowns using the overall system to start with. So, instead we can start with single systems. So, where do we start? In the previous example we started with the input stream because we had information about the feed which was entering. However, here we have information about the product which is being produced. So, it has been told that we are producing 1000 kilograms per hour of sugar. So, because we have information about the product stream, we can start from the last unit. So, we will start with the crystallizer as the system of interest to start the calculations. Before we start doing the calculations, we need to identify the basis for the problem. So, here there is only one flow rate which has been given, which is the mass flow rate of sugar leaving through the stream M. So, our basis for this calculation would be 1000 kilograms per hour M. So, let us start with the crystallizer. So, we need to now write the total balance and the component balances for the crystallizer. The total balance would be input equals output, assuming that the process is at steady state, and because it is a non-reactive process, generation and consumption terms go to 0, leaving you input equals output. So, the total balance will then be written as K equals L plus M. We know the value for M, we do not know the value for K and L. Now, let us write a component balance. The component balance we can write can be for sugar or for water. So, let us write for sugar. The sugar balance would be 0.4 times K is equal to 1000, which is M, plus 0, because sugar is not leaving through the stream L. So, using this equation we can calculate the value for K as 1000 divided by 0.4, giving you a value of 2500 kilograms per hour. So, substituting this back to the total balance equation, we can calculate L as 1500 kilograms per hour. So, now we have identified one system and solved the balances for K and L. So, similarly we can now choose the next system, which would be the evaporator. So, for this stream again we have the information about the stream K and the information about stream J, and the information for H is also given. So, we have the composition for all the 3 streams. However, the mass flow rate is known only for the stream K. So, this is exactly the same as what we did for crystallizer. So, as we did there, we will start with the total balance for the evaporator system as H equals K plus J, and we know the value of K to be 2500. So, this is H equals 2500 plus J. So, now we can write a component balance. So, here we can again write a sugar balance. So, the sugar balance would be 0.15 times H equals 0.4 times K. So, this would mean 0.15 H equals 1000, giving you a value for H as 6667 kilograms per hour. So, substituting it back to the values to the total balance equation, we can calculate J as 4167 kilograms per hour. Now that we have calculated the streams L, K, J and H, we can start with the system of screen to identify the mass flow rates of E and G. So, for starting that, let us first write the total balance equation. The total balance equation for the screen would be E equals G plus H, and then we can write component balances. Here we will first choose pulp as the component balance, because we know the concentration of pulp in the input stream E and the exit stream G. So, this makes it 0.14 times E equals 0.95 times G. As we already know the value for H, we can substitute this equation as G plus 6667. So, now you have two equations and two unknowns. You can solve for E and G and you would end up with E equals 7819 kilograms per hour, and you will get G as 1152 kilograms per hour. Now that we have the mass flow rates, we are not done, because we need to know the composition of the solid stream G which is leaving the system. Unlike the other streams which we looked at till now, this particular stream has sugar, water and pulp together. Why do we say that? You have 95% pulps, which means the other 5% has to be the liquid component which is accompanying the solids. This liquid component will not only contain the water, but also contain the dissolved component which is sugar. However, we do not know the composition of water and sugar in this mixture. We know that those two add up to 5%. So, let us assume that the composition of water in this stream G is XWG is the mass fraction of water. In stream G. So, assuming that, let us write a water balance equation. So, the water balance equation would be 1 minus 0.13 minus 0.14 times E. How did I get this? We know that the total mass fraction for any mixture would be 1, and in the mixture which is entering the screen, which is E, you have 0.13 or 13% sugar and you have 14% pulp, which is 0.14. So, the amount of water, the mass fraction of water would be 1 minus 0.13 minus 0.14 times E, which is your mass flow rate for the stream entering the screen. You now have the exit streams. So, the exit stream would contain XWG times G, where XWG is the mass fraction of water in the stream G, and you also have water leaving through the sugar stream, which is, or the H stream, which is 0.85 times H. Now that we have all these values, the only term which is unknown here is XWG. So, we can calculate the amount of water in the mass fraction of water in the stream G as XWG equals 0.036. So, how much of sugar is present in your solid stream? So, that would be given by the mass fraction XSG, which is 1 minus 0.95, which is the mass fraction of pulp in the solid stream, minus 0.036, which is the mass fraction of water in the solid stream, giving you the mass fraction of sugar in the solid stream as 0.014. So, this gives you all the information about these two streams. You have calculated the flow rates and also the composition of these streams. Now, we need to perform similar calculations to identify the flow rate and the composition of the bagasse stream, which is the stream D. How do we go about that? We identify mill as the system, and once we have identified mill as the system, we need to understand that we have all the information about the cane stream, which is the feed stream entering into the mill. We have all the information about the stream extract stream E, which is leaving the mill. However, we have only one information about the bagasse stream, which is the percentage of pulp. The other 20% basically contains water and the dissolved component, which is sugar. So, just like how we solved for the previous problem, here also we can make an assumption for the mass fraction of water in the stream to be XWD. Let us first start with the total balances. The total balance for the stream, for the system mill, would be F equals D plus E. We already know the value for E, which is 7819. So, F equals D plus 7819. Now, we can write component balances. We will start with the pulp balance. So, the pulp balance would be 0.59 times F equals 0.8 times D plus 0.14 times 7819, which is E. Using these two equations, we have two unknowns F and D, and we can solve for them. We will get F equals 24,574 kilograms per hour, and we will get D as 16,755 kilograms per hour. We still need to calculate the composition of the stream D, which is basically the amount of sugar which is leaving through stream D. For that, we will use the assumed mass fraction of water, and let us write a water balance for the system mill. So, the water balance would be 0.25 times F equals XWD times D plus 1 minus 0.13 minus 0.14 times E. So, this gives you XWD times D plus 0.73 times E. Now that we know the values of F, D and E, we can calculate XWD as 0.026, which means the amount of sugar, the mass fraction of sugar which is leaving through the stream D would be 1 minus 0.8 minus 0.026, giving you a value of 0.174. So, this gives you the composition of the stream D also. So, the stream D, which is the bagasse stream, contains 80% pulp, and it contains 17.4% sugar and 2.6% water. So, with that we have calculated all the flow rates and compositions of the streams. In addition to calculating the mass flow rates of each of the stream and the composition of these streams, we have also been asked to calculate the fraction of the sugar fed that has actually been recovered through this process. We know that the total amount of sugar which is recovered is 1000 kilograms per hour. So, considering the overall system, we know that sugar only enters through the cane and it leaves through multiple streams. However, we are concerned only about the crystal sugars which have been recovered, which means 1000 kilograms per hour of sugar has been recovered. The amount of sugar which is fed into the system through the stream F would be 0.16 times F, which is 0.16 times 24,574. This gives you a value of 3,931.84 kilograms per hour. So, the total amount of sugar which is fed to the system is 3,931.84 kilograms per hour, out of which only 1000 kilograms has been recovered. So, the fraction recovery would be given as 1000 divided by 3,931.84, which gives you a value of 0.254. So, about 25% of the sugar which has been fed into the system has actually been recovered. So, with this we come to the end of the example problems for multiple unit processes without reactions. What you would have learned is when there are multiple units, the system which is chosen for studying becomes the most important thing. By choosing the right system, the problem can be solved in simple steps. So, we looked at 3 different example problems. In the first one, we chose the overall system to start with, and in the second example problem, we started with the first system in the process, and in the third example problem, we started with the last unit as the system. By performing these 3 different types of calculations, I have tried to show you how we can attack such a multi-unit process. Hopefully, this will give you enough experience to solve such problems. I strongly recommend that you refer to the textbooks which we have been recommended and solve more problems so that you can intuitively choose the right system to study. Choosing the system is very critical, and that comes only through practice. I strongly recommend you do more problems and gain experience in identifying the right system to start with. Thank you.